All right. Let's continue our lecture. Right. Let me take a look. Okay. So I would say today will be our last physical lecturing. Okay. Maybe even for me, for myself. All right. Because yeah, last time, well, next time, well, I won't have next thermodynamics of solids, right? Because I'm going to change my job. All right. So I feel grateful, and then thank you for coming. Then next week I'm going to Australia for conference, so there's no physical course again, and then I will give you another video for completing PDF 9. All right, and then next week, suppose 17 of December will be your final exam, and then that's it. Okay, that's all for this semester. I should say sorry that because the only 16 weeks in our semester for the NYCU University, right? Right. As far as I know, some university may not have this 16 weeks policy, like Taipei Tech University. Well, I don't know if this is good or not, but it's easier for lecturers to, squeeze in all the teaching materials. Yeah, I think it's 16 weeks, a little bit rush, but yeah, it's okay. Right. So last time I gave you a video, right? The video is supposed to related to PDF 7, classical and statistical thermodynamics, about ideal gas. Okay, classical statistical treatment of an ideal gas treatment, right? How we look, how we observe the behavior of ideal gas, and then I will give you a quick, well, relatively quick review, because some of you, I hope all of you have watched the video, right? So in the chapter 6, we have done this, and I guess you are really familiar with this, right? Because you have finished the midterm too, right? You done the Z partition function, right, for Maxwell-Boltz's distribution. And this distribution valid for dilute gases, okay? So you use Z, and you use the well-known Boltzmann equation. You connect successfully with Z and S, all right? And then use the S as an entrance or bridge, and then you can determine F and mu and U. Okay, that's really good. And if you have U, and you can get the G, and if you have G, you can get, sorry, you have mu, and you can have G, and then you have G and T and S, you can get H, and then you have H. Then you can do the partial differentiation for F to get P. So as you can see, when you have S, you can get every property in material, and then you can compare the results with classical thermodynamics. And then we found that, okay, the partition function, the behavior of partition function can be seen like this: low T and high T. When a low temperature, you will have most of the particle occupied at ground state. And if you have a higher temperature, you will have more population of the atoms or particle to occupy the higher energy state. So it's reasonable, right? And then we substitute the translational degeneracy function, G. Remember, we using the particle in the box, right? And we determine the G. And then so we substitute the G into the Z, and then we can conclude that, okay, Z is proportional to volume, right? So you can see this Z and volume's relationship. Okay, and then we, also monotonic, because today we were going to talk about diatomic. Okay, diatomic was the double atoms in the molecular, but monatomic is just one single atom for the gas. Okay, and yeah, so you find that this is all the summary table for the mu, u, s, all the properties connecting to the z, and because of z equal to something relative to v, so you can obtain a beautiful, well, not beautiful, I mean, another form of all the properties. And beautifully, you can see that, wow, after you've done that, P equal to NKTV, NKT over V. So you can see that this is well connected to classical thermodynamics. Good. And then we found that, well, determine the sacred tetrol, yeah? And then we examine the Maxwell-Boltz's distribution is good or not. You can see that this is good. And then we combine the N and F, and then we can find that, well connected, I would say. After all the substitution, and by using statistical approach, by using Z and N or something, and then we found that, yes, this is really connected to classical thermodynamics. So you can see, you can obtain the same result by two different approaches. The first one is classic, the other is statistical thermodynamics, and you find that they're all the same. Okay? And then we found that the entropy of mixing, we still obtain the same result for the classical thermodynamics, but in the statistical thermodynamics, we can overcome Gibbs paradox, because in statistical thermodynamics approach, when you mixing two identical gases, and then their occupation number won't be the same, won't be different. They remain the same. So the choices are the same. So the Z won't change. So it can overcome the Gibbs paradox. So this is the better part. This is the advantage of the statistical thermodynamics. All right. Well, that's it. That's chapter 7. And then we continue. All right. Continue 8. Okay. And then we continue to the heat capacity of diatomic gas. Diatomic, which means that we have two atoms in the molecular. And then we need to talk about how is the energy stored in the molecular first, right? There are 4 types of energy. The first one is electronic energy, but we can refer to page 20. Okay, we can go skip to the page 20 first. I guess I did that right in the video. 20. Yeah, you can see that the spacing of the energy levels, we have 4 types of energy in the diatomic particle, diatomic molecular gas. You can see that we have translation, rotation, and vibration, and electronics. And you see translation moving around need a little bit energy. So, and also they have plenty of component directions, so they can be distinguished Okay, and you can see the translation energy level so packed, just like continuous. And then rotational, you need more energy to rotate. So you can see that the gap is relatively bigger than the translational, right? So you see wow, so packed. And then if you need to rotate and then translate, you need to giving more energy to jump to the next level of rotation. So you can see the gap, the scale between the rotational gap and the translation gap. And then if you want to do the vibrational, I think, I believe you also watched the video, right? The vibrational is also look like this, and then the vibration frequency. If you have higher energy, you got higher frequency. Okay, shaking, right? So each shaking energy level is even bigger than rotational matrix. So, sorry, not rotational matrix, rotational energy gap. So you see, rotational matrix is relatively, packed compared to vibrational matrix. So you see you can see the scale are so different. All right, so this energy level actually like this, right? And then if you want to go electronic excitation, you kind of moving entire vibrational energy landscape to the up to the next level, right? So you need many energy, much energy to excite entire things. You see entire things, anything inside this, you need to excite it to the upper level. It requires much more energy compared to the first three excitation. So in this course, we're not going to discuss this. All right. So we just focus on the kinetic energy, moving things. All right. Translational, no problem. We have done that in particle in a box. And rotational energy, we covered in the video, right? I believe you noticed that, you watched that. And then we are going to talk about vibrational. Sorry. We have talked about vibrational first. You've done that in the watch. You watched the video, right? And then today we are going to talk about rotational matrix later. All right. So another quick review for vibrational energy. You see the vibration is, we regard it as an oscillator. Oscillator is a spring with two atoms. Okay. And then shaking, vibrating. So if you have a higher energy, you vibrate quicker, and which means that you have higher vibrational frequency, nu. Okay, and really important things here is that the QM harmonic oscillator, quantum mechanics harmonic oscillator, has energy level in this form. And this form tells us something. The first one is GJ equal to 1 is non-degenerate, right? And all the degeneracy are 0. Are 1. Okay, non-degeneracy. And then very important thing is that you can see the energy is equally spaced. So J is kind of it's a constant, right? 1 or 2 or 3 or 4 variables, but it's a constant. So you can see that each energy level has spaced h nu. Very good. Very important thing in second one, the ground state. If you substitute J equal to 0 here, epsilon J is half h nu. So you see 0 energy at 0 point energy is not 0. Very important. 0 point energy is half h nu. So it's called never stop vibrating. Your seniors in past few years, they has difficulty to understand this. They think 0 point energy is zero. Okay, but in the quantum mechanic harmonic oscillator, this is not zero. Okay, careful. And this also makes something you need to determine in chapter PDF 9. All right, so if you missing this, you're losing some turn in chapter PDF 9. All right. And then we found that, oh, this is distinguishable because the energy is so, the translational quantum states are so packed. So you can always find your own direction. So you can identify particles by different translational quantum states. So we can regard it as a distinguishable. When you regard this distinguishable, you can have Boltzmann statistic. All right. So you see that when we talk about chapter 7, we talk about, we determine a lot of Z, S, F, mu, and don't forget, this is so important. Another important thing I want to mention again and then again. The formula we mentioned in the course, in the lecture, or in the video, we all focus on Maxwell-Boltzmann distribution in the PDF 7. Okay? Maxwell-Boltzmann distribution is only for dilute gas, but sometimes, for example, in the midterm 2 or final, sometimes we have questions. We asking you to do other distribution, not Maxwell-Boltzmann, maybe other distribution. You cannot just memorize all this and then write it down. No, you should using the same method, the same procedure to using the Z to determine, because you won't have the same Z, right, for different distribution. So you have this different Z, so you will have, suppose you will have this different S and F and nu and so on and so forth. So this is really, you need to be really careful about this. Okay, then we discuss about the oscillator for Boltzmann statistic, right? And then we introduce a really useful mathematical tool. It's called 1 + y + y squared y cubed, etc. equal to 1 over 1 minus y. This is so important, right? So useful later, okay? And why? Because if you just make this to the left-hand side, to the time this to the left-hand side, you find that everything can cancel, become 1. All right? So this is so important. It simplifies this form into, well, I mean, 1 over 1 minus y things. Okay, so this is quite useful. And yeah, they have similar behavior that if you have a higher temperature, you occupy higher. If you have higher temperature, all the particle will excite to a higher level. And also, this also introduce that the theta is characteristic temperature. So you can say that the temperature is you can refer the temperature by how many times of your characteristic temperature. Okay, for example, half of characteristic temperature, or double your characteristic temperature. So the characteristic temperature is actually different from all the materials. All right. So it also can be regarded as a kind of activation. If you pass the theta, which means that you have higher chance to activate. If you below the temperature of the characteristic temperature, which means that typically this degree of freedom is locked. It's not activated. All right. So that's it. And then, yeah, and then interestingly, if you have this equation in the ancient age, we don't have computer, right? So typically they examine the equation by using some extremal condition like high temperature, low temperature. In the middle, you can calculate that, but you need to using your hand, and then so it's really tired. Okay, so in the textbook, they typically examine low temperature and high temperature. Right. So in the low temperature and high temperature, you can get some results, and then of course, this page tell you a really important mathematical tool. Later we will use like in page 13. All right. So this is important. When x is much less than 1, your exponential x approximately equal to 1 plus x. So important. And if x much less than 1, your x is approximately equal to natural log 1 plus x. Well, you can see this is really similar. I mean, they are the same, okay? But we will use this in page 13 later, all right? Almost done for the summary. We spent like 30 minutes to summary because I gave you the video. So I want to ensure that everyone has an idea what we talk about in the video. All right, and you see, high temperature is kind of like 2 theta things, 2 times of theta, 2 times of characteristic temperature. And for example, it will be kind of excited. Okay, but if this is below like half characteristic temperature, it is not activated, and it becomes 0-point energy, half h nu. Okay. Then another important thing is that we know the U, so we can determine the heat capacity, right? So we do the differentiation, and then we can get this ugly form. But now, because the theta is characteristic temperature, right? Now we only focus on vibration. So in the case that we are going to use another characteristic temperature for rotation or something, we are adding VIB vibrate for the characteristic temperature for vibration. All right, theta VIB. Okay, and then we use the high temperature, low temperature, some mathematical tool we introduced later in the previous page. We can get high T is NK and low T is something. The low T is so ugly. The CV in the low T for vibration is so ugly here. NK theta over T blah 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 square and exponential. Oh, it's so ugly. So now I use green highlight to highlight this ugly form. And then actually this is not really, terrifying. If you write down like x squared exponential minus x, and then if you using your Excel, and then you substitute the x, you can get this figure. And then this figure, and then we found that our low temperature T over theta much less than 1, which means that theta over T inverse much greater than 1. And what condition looks like? It actually going to very small approach to 0. Okay, so yeah, which means that is this form going to 0. Okay, so going to 0, CV approximately to 0. See? Okay, so frozen and excited, actually just controlled by temperature. Okay, so remember this green highlighted function. Remember that when theta over T much greater than 1, it will become 0. Okay, just remember this, and then we will use that later quite frequently when we see this, I was highlighted in the green. Okay, no problem. Now, okay, so I ask you to finish the course at this point, right? So I'm going to officially introduce life, okay, in front of you. So let's continue our lecture in here. Okay. Wait a bit. Right. Okay. Empty, blank. Note. All right. So let me think of it. 那其实我讲过，就是下礼拜是我要去澳洲。好，我刚刚花30分钟讲那个 video 在上什么课了哈。当然，我相信大家都已经看过了哈，一定要看哦，不然的话现在应该听不懂。所以我刚刚花了半个小时，就是快速的 go through 第7章 PDF 7跟 PDF 8的一半。那这一次是我最后一次上课，那最后一次上固态热力学。好，那非常感谢大家的参与，然后接下来应该就没有这门课啦。应该说其他的老师可能会开了哈，但是我就不会开了。然后感谢大家，然后下礼拜我要去澳洲开会，所以就也是 video， 但这个 video 应该看一下就好了，因为第9章就上完，PDF 9上完就结束了嘛哈，所以我今天应该可以上到第9章多一点点。那所以其实下一次上 PDF 就是 video 就只要看一点点就好了。那再下一次就是期末考了，那期末考完就大家再见。然后16号理论上来讲，立军会把助教会把考卷就是线上发给大家这样，或是请大家去他的实验室去拿这样子。OK， 大概是这样。好，那我们就开始上课啦。Alright, let's continue. So next we're going to talk about rotation. Rotation is I hope you took the mechanics of material course 材料力学. There's something there's the term called mass moment of inertia in that course. We define that. So this is actually a bachelor college level stuff. All right. It's called mass moment of inertia. It is the definition for this is that a measure of the body resistance to angular acceleration. Wow, this is still difficult. I will say this value is the value that describing how difficult this material can rotate. Okay, so if this the value of mass of moment of inertia is big, it means that it is really difficult to rotate it. Okay, and the rotation is also related to the axis. Okay, for example, I always, if you took my mechanics of material course, I talk that if this material going to rotate, okay, is that easier to rotate along the axis, penetrating to their centroid. So yeah, this is easy, right? Easy to rotate. But if you rotate with this axis, this is really difficult, right? This is not difficult, not easy. So which means that the axis also affects the mass moment of inertia. But in the real world, I mean in the atom gas, they rotate. Suppose they rotate in along its centroid axis, so it should be okay. And also another thing is that the centroid also related to two particle distance. So you can imagine that ballet dancer, okay, or sorry, should be skating dancer， 滑冰的舞者 ，when they rotate themselves, they start to open their arm and rotate, right? And when they want to speed up their rotation, they close their arm to the chest, right? So when they close to the chest, they will be faster, right? So which means that mass moment of inertia is bigger when they rotate like this, and smaller when they rotate like this. So it will rotating faster when the mass moment of inertia decrease. Why? Because their radius, their diameter decrease. Okay, their mass of that distribution of that diameter is decreased. So you can see that they will be the R1 and R2 will be related to the how easy to rotate. Okay, so yeah, that's it. Let's take a look. So the mass moment of inertia is related to rotation, just like your translation related to mass, right? The mass, when you trying to move something, how difficult for the material to resistance to the move, the mass, right? If you have bigger, heavier things, it's difficult for you to move. So translation is related to mass, but rotation is mass moment of inertia. Okay, so these two things are kind of the same logic. All right. So you see the resistance, the R squared. The R squared, R means the arm, right? When your R is bigger, your I is bigger. When your R is smaller, your I is smaller. Okay, so this is the definition of the mass moment of inertia. R squared times the M, the mass distribution. You need to do the integration for that. So this is the things that we're going to measure. Okay, so mass moment of inertia is here, and also the X is generally chosen, which pass through the body mass center, centroid, right? Which has N1 R1, N2 R2. Okay. When the for how to determine centroid of the volume, you can see that especially for the particle. This is for general volume, then this is for two particle, because nothing here, right? Nothing here. The particle only, the molecular, the object only has 2 points, N1, N2. So N1 times R1, N2 times R2. We want to find the centroid. Okay, so the moment should be balanced, right? So N1 times R1 need to be N2 times R2. Okay, and then so R0 is R1 plus R2, no problem. And R1 should be when you substitute this into, you can substitute the R0 into this, and then you can find that R1 equal to M, the ratio R1 equal to R0 times M2 over M1 plus M2, and R2 equal to R0 times M1 over M1 plus M2. Okay, so R1, R2, we got it. And then if we summation all the M1 times R1 squared, N2 times R2 squared, sum them up together, actually it will become N1 times N2 over N1 plus N2 and R0 squared. Okay? And we will call this mu. It's a kind of the mass of the two atoms. It's a reduced mass, effective 等效的 mass. Okay? So your I equal to this. So now you know how to determine the I here. OK， 好，我们现在讲就是 惯性矩啦哈。惯性矩我们在材料力学就有上过，我希望你有上过材料力学。那材料力学的时候有说过，惯性矩的意思就是一个物体要要转动一个物体有多难的意思啦，越大就越难。OK， 那我们刚刚有快速的讲到，就是滑冰的舞者他不在转的时候，一开始是把手是张开的吗？也就是他把他的质量，这边手臂的质量的分布变大嘛，对不对哈？然后变大完以后，它就会变得比较难转，所以转比较慢。但它要加速的时候，就把手质量放回它的那个行星的转轴，所以它就越来越快越快。同样的力量嘛，它没有加力量啊，哈，它就会越来越快。好，那就是 rotation 的这个惯性矩的意义。OK， 那转动就之于惯性矩，那就像是移动之于质量。你要移动一个东西，越重就越难移嘛，对不对哈？那所以这个 mass 就跟 mass momentum of inertia 是相同逻辑的。OK， 等一下也会看到。那我们在转的时候，当然会现实生活中那些气体就只有两颗分子结合在一起嘛，所以他们就只有两个质量在两端，他们转的就是都会绕着它的最好转嘛，就是在它的行星的部分转。那行星在哪里呢？就是 n1 乘 r1 等于 n2 乘 r2。那这是标准的行星的找的公式。找完以后，我们就发现 r1 r2 是跟它的质量的比例是有关系的。我们找到 r1 r2 以后，代入这个公式。那当然这边是 summation， 那其实因为这就这两颗嘛，所以就是 summation 就不是这是 integration， 这是 general， 这是一般性的形状。但是如果今天只有两颗，那就只要加起来就好了。OK， 那我们就把 r1 平方 n1 加 r2 平方 n2 加起来以后就长这个样子。那这个东西叫做等效的一个参数了哈，等效的一个质量，不过这不重要。总之这就是惯性矩的介绍。So next we are going to use this I. So I equal to mu r naught squared. We just learned that, right? This one, I mu r naught squared. Okay, we've done that. And what is rotational energy? Rotational energy becomes half I omega squared. Wow, what does that mean? Don't worry. If you understand mass, you will understand this. Translation. If you understand translation, you will understand this. Translation energy equal to half mv squared, right? So do you think this is really similar? When I say they have the same logic, right? So again, translation, momentum, okay, equal to P equal, sorry, equal to, P equal to mv, right? So, you see, P squared divided by 2n is also translation energy, right? So, we can say the L squared wait a minute. Okay, so angular momentum is n v omega. Omega is angular velocity, right? Omega. So omega is angular velocity, just like the translational energy v. Okay, so half I omega squared equal just analog to translation energy half mv squared. But translational momentum P equal to mv. So angular momentum will L equal to I omega. Okay, so you can compare this again. All right, and after you compare, you can say P squared over 2m is L squared divided by 2I. Okay, so that's it. So when you know the translation, you know the rotation, how it works. Okay, so angular momentum I omega, right? Now, let's get into the quantum mechanics, all right? So when the quantum mechanics solves the Schrödinger equation for the rigid rotator, okay? And their quantum energy level, epsilon L, equal to L times L plus 1, and h bar squared over 2I. Okay, I don't know why. All right, I mean, we just use the solution for the Schrödinger equation for the rigid rotator. Okay, so we use that, right? And also we also has the what is L? What is L? L is orbital quantum quantum number, just like previous n, okay? But here L means the rotator. How the rotate? So how many possibility for the rotator can achieve the different energy? Okay, so you can see that the orbital quantum number is also in this energy level. Okay, L times L plus 1, blah 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 blah. And you see the L squared. Okay, you see in the quantum mechanics, they found that the square of the allowed angular momentum is L squared equal to this one, L times L plus 1. All right. Well, I cannot prove that. They prove in the 近代物理要怎么讲？近代物理 recent recent piece. I don't know. All right, so they solve that and we just use it. Okay, it's not a scope in this course. So they found that the rotation energy is actually related to the orbital quantum number they have. Okay, if they have higher L, you will have higher angular momentum. All right. So if you have higher energy, higher angular momentum, you substitute here, you can find higher rotational energy, L squared over 2I. So this is L squared L squared over 2I. So they are the same. Okay, rotational energy. Right. So again, if you have rotational energy, for the energy, each energy level, writing down like this, epsilon L, you can find that we want to find a characteristic temperature to activate the rotation. You find that, okay, h bar squared 2I over k will be the form like the characteristic temperature. So you can write down like this, L times L plus 1, K theta rotate. Okay? And the theta rotate, just like the theta vibration, they are different, but from different materials, different gas. And the theta rotate can be found, can be measured by infrared spectroscopy. Wow. So this is kind of material property that you can measure. OK， 好，那赶快2分钟翻译一下，就是我们都已经知道， 不是惯性矩，惯性矩是 I 嘛，好，它跟 mass 几乎有类似的逻辑。好，那我们就想要知道 rotation energy 到底是多少？那 rotation energy 怎么样？就是1/2 I omega 平方。哦，这个你应该没问题，因为你会 translational energy 1/2 mv 平方，所以 omega 是角速度嘛，那 v 就是一般的速度嘛，那 I 就是惯性矩，m 就是一般的质量。那动量呢是 P 等于 mv，这你也没问题。所以 L 大写的 L 就会是 I omega，I 不就是对应到 mass 吗？omega 就对应到 v，所以这个 L 没问题。然后呢，translational 的 energy 可以用二次方的动量除以2m，那不就是 rotational energy 也可以用写成 L 角动量的平方除以2I 吗？好，所以我们知道这个 rotational energy 就长这个样子。那接下来我们要看 L 平方是什么？L 平方呢？这个在近代物理有解过，确定的方程是它的 rotation 的话，它的 L 的energy 的 level，它是被 orbital quantum number 控制的，就跟我们之前的第一阶、第二阶的 n 一样。好，那所以它的 L 平方，它解出来的是长这样子。那 L 平方，那我们就把它带到上面去，就可以得到这个东西除以2I，就会是我们每一个 energy level 它 rotation 的该有的能阶。那这个能阶，我们的这个，我们就发现，哎，其实 theta rotation 就是一个 characteristic temperature 嘛。那我们用前面的形式，就是我们就可以把它写成2I 除以 k，就是它这是一个温度的表示方式，然后把它带入进去以后，就可以把它写成这样的啦。那所以我们的 energy level 就会是 L 乘上 L 加1 k 乘上 theta rotate。那等一下就可以用这个 theta rotate 去看它有没有 activate。OK，好，那我们今天先给大家20分钟的下课时间。I will see you after 20 minutes. Thank you. Wait. Okay, we'll come back. Right, let's continue our lecture. So this chapter PDF 8, we just done the energy level, all right, for each rotational energy level, right? And next, let's talk about the partition function for rotation. Okay. Okay. So when we after we done the quantum energy level expression, and then we are going to write down. We have done this, right? This part, and sorry, this part, and then we're going to get G. G is degeneracy, right? The degeneracy GL is that state for energy level for level L corresponding to different possible direction of the angular momentum vector. What does that mean? So when you have a rotator like gyro, all right, you twist it, you rotate it, and it like vibrating. You can imagine that if when you do the higher energy, you rotate faster, you may have more possible angle. Stay that at possible angle to see the rotating angle may have more choices. But if you rotate slowly, it quickly become the center, right? So which means that if you have different rotating force, you may have different choices of the angle of the gyro movement. So it is the case that if the L equal to 2, which means that you have certain 1, 2, 3, 4, and 5, 6, I guess. 1, 2, 3, 4, 5, 6. Okay, so n equal to 2 is, so quantum mechanics solve that the GL equal to 2L plus 1. So if you have L equal to 2, you have 2 times 2, 4, 4 plus 1, 5. Okay, so you have 5 degeneracy in L equal to 2. So 1, 2, 3, 4, sorry. 1, 1, 2, 3, 4, 5. All right, is that right? Yeah. 0, 1, 2, 3, 4, 5. All right, so you got 5 choices. 1, 2, 3, 4, 5. 2 times 2 equal to 5. 2 times 2 plus 1 equal to 5. All right, so this is how they solve that. All right, so you substitute this GL into here, you got Z equal to this one. All right, so now after we have a Z, we can examine this in high temperature and low temperature behavior. So let's take a look. So when the high temperature, which means that temperature much greater than theta, rotate. So so you can see let x equal to L plus times L plus 1. So your equation becomes Z equal to this. Okay. And you can, and also you see this is a summation, right? But because your temperature means is really high, so which means that there are many states that can be excited. So many closely spaced energy state can be excited. So you have many excited states. So looks like a continuous. So summation become integration. Okay? And then the form like this. So we can continue to 1 over t, theta rotate, integration 0 sigma. And why do we do this? Because we change the variables. Previously, this is dx, but now we change to the exponential minus theta. I rotate x over t. All right, so we make this one to change the variables, okay? And try to make the integration works, right? So minus t over theta rotate equal exponential minus theta rotate x over t. But don't forget, we need to substitute some the boundary, upper boundary and lower boundary. After that, the answer is t over theta rotate. Okay, relatively easy. So when your temperature become higher and your z become t over theta rotate. Okay, we will use this in the next page. And high temperature behavior. This is low temperature. Low temperature behavior when T much less than theta R over T, theta R O T. Okay, so we just write it down because this is summation, right? Z equal to when we substitute L equal to 0 and 1 and 2 and 3. Okay, so after we substitute all the, one item by each time. So the first term is 1, the second term is 3, blah, 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 and 5, blah, 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 blah. So we have many terms because this is summation, right? But this is interesting, okay? All the molecules are in the fuel lowest level because you are in the low temperature state. So we're actually the third term and fourth term and final term and etc. is not relevant. Okay, so we just need to consider the first two terms. Is because this is low temperature. This is really difficult for energy to particle to excite to the higher energy level. So actually, we can not consider this higher order term. We only consider first two terms should be okay because it's low temperature behavior. Okay, so now here 1 plus 3 times exponential blah blah blah. Okay, interestingly, this one, because your temperature is much less than theta ROT. So this is minus, right? So this is small and minus exponential minus small value. So it's very small. Sorry, minus big number. So this is really small, very small. Of course, much less than 1. So now you see natural log z, natural log 1 plus 3, these three things become 3 exponential minus 2 theta rotate. Why? Because remember, natural log 1 plus x approximately equal to x when the x much less than 1, right? In the page like A, I think. So after that, we can substitute this into the u things. U equal to nkt squared natural log z partial over partial t, right? So now we can directly obtain u. So this z and this u, we will use that later, all right, in the next page. OK， 好，我们现在要讲的就是，我们把前面的那个 quantum energy level 已经算出来了，接下来我们就要看 z 嘛，这个 z 也就是 epsilon l 已经算出来了 ，OK， 那接下来看我们的 degeneracy G， 那这个 G 又是什么呢？这个 G 的英文的翻译哈，就是有点绕口了哈，就是它的角动量的向量有几种不同的可能的方向 ，OK， 那我们就可以想象一下，就是一个陀螺哈。你在转的时候，你慢慢转，它可能就一转就转完以后就一转，它就好好的转，转完以后就倒下来。但如果你今天是很用力的转，它很快，它可能会是先偏的转，然后到后面才回到正的哈。所以也就是说，你速度越快，你的那种角度可以是越倾斜的，那就等于是越多选择。那这边就是这边的角度选择，你可以是平的转，然后一阶。2阶，好，大概是这样子。那当然，这边虽然怎么会是往下呢？没有啦，它其实是这样子的意思啦。它其实是你可以是这样子转，也可以是这样子转，也可以是这样转，也可以是这样转。OK， 然后所以你会有五种可能，所以应该是1、2、3、4、5，好，这样转。OK， 好。那转完以后，你就会有这5种选择，所以它的GL 等于是2L 加1。像这边如果你有 L 等于2的话，你有2阶的话，就像刚刚讲的，第一种转法，第二种转法，第三种转法，第四种转法，第5种转法，就这样。OK， 所以有5种，2乘上2加1就5个。好，那终于有这个 degeneracy 啦，那把它带进去就得到一个 z 很丑的公式。接下来我们就要看 z 的高温的行为是什么。好，那高温行为表示说它要考虑非常多的阶嘛，对不对？哈，因为它很高温。那也就是说，我们可以看到刚刚那个 rotational 的那个能阶，其实都是满满的连接在一起，它其实 closed pad 它是靠得很近的。那我们可以把它视为连续的。那因为这边是 summation， 你要加太多了，不如把它视为连续的，所以你把它变成0到无限大的积分。好，我们算出来以后。我们就这边是一个 exponential 嘛，所以我要把它积分的话，就要把变数转换一下哈，变数转换成这个，然后就变成1了，然后得到这个式子，然后算一算，算完以后把上下界带进去，就得到 t 除以这个 theta ROT。好，这个等一下我们会用到 z 在高温的时候它会等于这个值，等一下会用到。那接下来 low t， 那也就是 t 远小于 theta ROT 嘛，哈。那这时候我们就知道说这是一个低温的现象，低温现象我们就开始就直接其实就把它列出来就好 ，z 就直接把它列出来，把第一就这个东西哈，这个东西第一项L 等于1，然后 L 等于2，L 等于3，把它全部这样带入进去，就可以得到1啊、3啊、5啊，这样这样算下去，我们只是纯粹把它列出来而已。那列出来以后，后面这一大堆怎么办？其实没有关系，因为这是低温的状态。低温的状态的话，后面其实不太有可能让它就是激发上去嘛，所以其实后面就不用考虑了，我们只要考虑前面这2个就好了。所以这算是一个技巧啦哈，所以考试的时候可能会用到哦哈。当你在 rotation 的时候，在低温的状态下的时候，你要写出来这个式子，你就直接把列出来，然后把前面2项考虑就好了，后面那项就不，后面那些大项就不用考虑了，因为他们不会被很少机会被激发上去。好，那这 z 等于是这个东西的话，那这时候就算完了。可是呢，等一下要算 heat capacity 嘛，哈，那我们就先把 U 算出来。那 U 的话要使用 natural log z 对不对？哈，所以我们就先 natural log z 一下，我们就把这东西前2项放进去。那我们又会发现，哦，这个3 exponential 负2 theta ROT 这个东西除以 t， 它其实非常的小。为什么？因为你的 theta ROT 非常的大。所以大的负的很大 ，exponential 负的很大，就会变得超小，对不对哈？所以说它这边也是就是会是一个非常小的一个值。 那非常非常小的值就当然是远小于1咯。还记得我们的 natural log 1加 x， 如果 x 远小于1的话，这个就约等于 x， 对不对哈？所以这个就约等于这个粉红色的东西，然后代入进去以后，我们就会得到 u 的值。好，那等一下我们就要用到这两个东西。Alright, so we will use this and that. This is for high T, this is for low T. Okay, so now this is high T. So this is a high T, right? T over theta RT, T over theta RT, natural log T over theta RT, and do the differentiation. What is the result? 1 over T. Okay, so 1 over T, after that become NKT. So when temperature is so high, your URT become NKT. And then your CVRT will be just do the differentiation. So become NK, easy. Okay. Yeah, so you see the rigid rotation exhibits the separation of energy between 2 degrees of freedom because each degree of freedom is half NKT, right? So CV rotate become, in a high temperature, become NK. Now, for the low temperature here, okay? You substitute this into here, the U become NKT squared. Okay, so that's the pink one. Okay, the pink one doing like this. So U rotate in low temperature looks like this. And then we do the partial differentiation for T, which is CVRT, right? We want to get the heat capacity. So 3NK, oh, so ugly. 2 theta RT divided by T, 2 exponential minus 2 theta RT over T. Okay, so ugly, right? But don't worry, we found our friend green highlighted part. Okay, green highlighted part. What does that mean? This. Remember that? This one with shape like this, and your theta over T is much, much greater than 1, right? So it will go to 0. T going to 0, your CV ROT going to 0 as well. So you see page 10. So you can get a similar green highlight behavior. Okay, so now you see when the temperature is high, the behavior of CV is NK, high temperature. Like 2 theta RT, 3 theta RT, they're all NK. But if you have low temperature, it becomes 0. So it will, go back to 0. So T over T to 0, CV RT become 0. Okay, so that's the behavior of the heat capacity due to the rotation. 好，我们刚刚不是在前一页算了 Z 在高温的时候是 T over theta RT 吗？然后在低温的时候，它是 Z 长这个样子，一加很丑的东西。可是实际上我们目的是要算 CB 嘛 ，heat capacity 嘛，哈，这一章节的题目就是 heat capacity， 对不对哈？那所以说我们的 Z 也要把它变成 natural log Z， 然后要带入进去让它算 U。好，那我们的 Z 呢带进去以后，算出来就是 U 是被粉红色了哈。好，我们这边要用，所以粉红色就在这里，这是它刚刚的答案。那我们刚刚的 natural log Z 在这里嘛，对不对哈？所以 T 除以 RO over T Z 除以 Z 西塔 ROT 的 natural log 做积分，做微分就是1 over T， 那 UROT 就变成 NKT， 很漂亮。那 NKT 很漂亮以后做微分就可以得到 CV， 就是 NK。所以高温的状态下，转动的因为转动的得到的比热，因为转动激发的比热会是 NK。好，那这个东西 low T 的话，就是刚刚的粉红色带入进去了嘛，哈，那 U 一样要做 T 的微分，就我们算出来这个很丑的东西，但是不用担心，后面这个绿色的东西啊，就是我们刚刚在第10页看到的，它的它的那个 curve 会长这样子，而且当 x 越大，它这个值就会越小，接近为0，所以这个东西会当温度就是西塔 ROT over T 变成很小的时候，很大的时候，它会变小，变成0这样子。那可是你看啊 temperature T 很小嘛，所以这个东西就变很大。那很大的话就接近为0 ，OK？所以它在低温的状态下，它就会为0。好，你就看到它会有在diatomic 的 gas 里面，它会在低温的时候被锁住，freeze，然后到高的西塔 ROT 之上的时候，就变成 NK 被 excited， 被激发上去。All right, next, this is really important. All right, so you got the result NK and 0, no problem. But this is the textbook, page 2A6. Very vague, very not clear. Okay, when it talk about homonuclear molecules, okay, when they talk about nuclear molecules is, which means that you have the diatomic gas with the same atom, like H2. I don't know why it's so blurry. H2. Okay, the H2. So which means that it said the result is too large by a factor of 2 for homonuclear molecules such as H2. What does that mean? And it said H2O2N2 for 2 identical nuclei. 2 opposite positions of the molecule are corresponding to the same state, blah, 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 blah. But it said the slight modification, no effect on thermodynamic properties of systems such as internal energy and heat capacity. Okay? He said, the author said, when you have 2 particles identical, for example, H, previously you have N1, N2, which means that they are different material, different atoms, but now you are homonuclear. So this is H, for example, H2, H. Okay, so now this is N, N. They are the same. Okay, so previously it was A and B, but now it become the same, H and H. So what does that mean? The result, the Z, are too large by a factor 2, which means that the possible states should be divided by 2, because your H here, if you rotate, they are the same. But if previously this is AB, you rotate, become BA, they are different. Okay, so H and H, you rotate the same. So your possible state need to divide by 2. So this means Z. Previously in high temperature T over theta ROT, right? You need to divide by 2. That's the meaning. That's the meaning of the homonucleate. moleculars. Right, so you see, if you have 2, and this U and CV is identical to this. The only difference is here has 2. Okay? Then, interestingly, after you've done this, you still got UROT, NKT, and CV, NK. So they are the same. Okay, so it said, 这什么东西啊？等我一下啊。Okay, so now you see the textbook said for the homonuclear moleculars, even you have the half Z, your U and CV won't affect. But I think this is really bad explanation. It said no effect on UROT and CVROT. Yes, it is true, but how about FROT, SROT? Please go home to do this. All right, you will find that it actually has effect. It actually has effect on FROT and SROT. So I really don't like this textbook. It's kind of misleading, right? 好，我要讲中文了，就是现在要讲单原子的双原子气里面只有单种原子的 ，OK？ 就例如说 H2O2N2，OK？ 我们原本在讲的东西是我们假设它是不同的2颗，所以它们的 Z 就这样算出来以后，算出来了。它的课本上面写说，这个结果对于单种原子的双原子气体是，他在讲什么？太大by 两个 factor， 所以我看不懂啊，看不懂。但我们仔细想一想看，就是说这个原本 A 跟 B 它在转的时候，你看它转过来就变成 B 跟 A 了，就是不一样，对不对哈？但是现在是 H， 如果两个都一样，你转还是一样 HH， 所以表示说它会有一半的可能性就不见了，因为它们转的还是一样嘛，哦，所以说这个是太大了，因为它对于是 A 跟 B 不同的原子，现在是 H 都一样了，那它就要变成少一半的可能性，所以就除以2。然后它之后，我觉得最可恶的是最后面，它后面写说这个 Z 变成2，除以2了，然后你代入进去算，发现跟我们的 C， 他说这样子的改变对于热力学的性质，像是 U 跟 T capacity 不会改变 ，no effect， 它上面写的 no effect。对啊，没错啊，的确，你这样代用进去，做完微分以后，然后算，哎，的确真的是没变哦，真的是没变可是重点在于你的 FROT 跟 SROT 会变呢，但他这句话写的很让人误解哦。他说 thermodynamic properties 只有这2个不会变，好不好？但其他的会变啊，他很坏，我觉得这个作者不知道在干嘛哦，真是的。所以回家去算算看 ，FROT 跟 SROT 是不是真的有改变？好，会有改变哦。等一下你就知道了。等一下吗？反正你看看就知道了哈。应该说，等一下我会带大家算 A 跟 B 不一样的状态下的 U 跟U 已经算完了，所以我会带大家算 F 跟 S。但是如果今天是，我等一下会带大家算吗？好像不会。好像不会，不过没关系。第七章我已经带大家算过了，你就会想想看，第七章如果今天你的 Z 少一半的话，会怎么样？好，那就这样。Okay, so I encourage you to using half Z. to determine F and S rotation. All right, they will change. Okay, don't trust the textbook too much. All right, so now let's enter electronic excitation. Well, we always talk about 0 and 1 degeneracy of the bond state, okay? And theta is so big, okay? So big, like, how to 120,000, okay? Oh, all right, so which means that this is so big, all right? So we are not talk about this. This is really difficult to happen in the real world, all right? 那我们接下来讲就是这个 electronics 激发哦，实在是太高了，它需要这个西塔一需要哇12万 K 啊，这真的超高的。好，那现实生活中几乎不会发生，也不是不会发生，就是你必须要人为去做这件事情，所以这很难。好，那我们就先不考虑了哈。Okay, so now after we finish all the four energy, we can talk about heat capacity for diatomic gas. Now, CV equal to translation CV plus rotation CV plus vibrational CV. Okay, so typically in the room temperature, here, about 273, is that correct? Or 300 anyway. Room temperature, okay, it's around here. So you can see that typically translation and rotation are excited, okay? So you can imagine that the temperature, this is theta ROT typically for the H2, all right? So theta ROT is here. So previously translation is activate, and another after activate room temperature, right? It activate the second rotational degree of freedom, but the vibrational is not activate. So that's the reason why here. So this is CVTR. This is CVROT, and this is CVVIB vibration. Okay, and if this this temperature is greater than its own characteristic temperature, it will be activate. They will start to activate. Okay, so translation, no problem, always activate. 3 over NR. So this is 3 over NR. All right. And here, as we can see, room temperature is higher than theta ROT, so it's activate. So for rotation, it's higher temperature. The higher temperature is what? NR, right? So it's NR. And then, so 3 over 2 NR plus NR is 5/2 NR. So this is the value that we typically obtain. But in the real world, not real world, in the room temperature, this one is not yet activated. So what we will say, this is locked. This is locked at room temperature. Well, at room temperature, at this vibrational value. But if we are going to higher temperature like theta ROB here, it will become activate and activates MR as well. So it will be 7/2 MR. Okay, so after the theta vibrate, it will start to become 7/2 nr. So the characteristic temperature of the bond depends on the bond strength between the two atoms. So which means that it can activate within a higher temperature, 5,000. Oh, so big.好，那我们前面把 translation 已经算完了 ，translation 就是最基本的，它一定基本上都会动嘛，所以就是3除以2 nr 这个没有问题。那 rotation 的话呢，我们在室温的状态下 rotation room temperature， 那 room temperature 的话，它已经比西塔 RT 高了，对不对？所以它已经开始在启动，所以 rotation 的 CV 对它来讲就是已经启动了，就是高温了，所以就是 NR 的状态 NR， 所以 NR 加2/3 NR 会变成5/2 NR， 对，然后这就是我们一般看到的 H2， 那也就是为什么我们之前不是有说过，我们用算的就发现，哎，算出来明明就是7个 degree of freedom， 怎么在室温下我们量出来的只有5/2 NR， 没有，不是7/2，很奇怪。好，那就是因为这样子。那7/2 NR 在它的西塔 vibration 是超过5000的，所以超过5000以后，它就会被 activate。它就是这个公式的现象就会趋近于 NR， 所以它就被驱动了。所以如果今天是在红色这个 room temperature 的时候，这边写的是 locked， 就是比较小的。OK， 好，那大概这就是这样子。So now let's talk about the total energy. Wow, it's kind of a review. You can see epsilon equal to epsilon translation, rotation, vibration, electronic excitation. All right. And this is really high, of course. And epsilon translation, I guess you know that we've done this in particle in the box. This is just a review. You have done this before, right? And n equal to 1, 2, 3. And you can see that in PDF page 5, page 34. And you are quite familiar with that because you just finished the midterm 2, right? The epsilon L is for rotational degree of freedom. L plus 1, 2I, one constant with R squared. Okay, for linear molecules. Right. And for the vibration, J plus half H nu. Okay, so that's the energy level expression for translation, rotation, and vibration, respectively. All right. 好，那我们这边只是做个总结。它所有的能量，它会是 epsilon 等于它的移动的能量、转动的能量、振动的能量跟电子激发态的能量，然后这些 epsilon 每个叫什么？每个能接的写法，这 translation 的话就是在 particle in the box 这一节有跟大家讲，然后今天我们也介绍了旋转的 rotation 的 epsilon L， 然后在叫什么？在录影带，在 video 不是录影带，现在没有在看录影带哈，看讲录影带就显自己很老这样。epsilon J 这是vibration 振动的，然后是 J 加1/2乘上 H nu。好，就这样。And then yeah, we actually we talked about that before. We're just saying that the vibrational energy is actually equally spaced, right? Equally spaced. Ooh. Equally spaced. And the group 0 point energy is H nu over 2. Well, just another emphasis to put some emphasis here. 那我们现在就是说，就其实这都是 review 了哈，都已经是复习了。我们这边只在再次强调说，在 vibrational energy 这个 energy level 里面，每一个 energy level 都是相同的宽度，哦，相同的 space，相同的间距，好，h nu，然后最重要的是零点能量是 h nu over two，不是零，好，这很重要。然后这一我们讲过了。This page I have been mentioned today in the beginning of the class. So actually we finished chapter 8. Sorry, not chapter 8. PDF 8. PDF 8. And then I noticed that in 2022, I adding one page in this PDF 8是这个东西。And now I'm going to talk about random things, not a big deal. I just going to share the story that I experienced in the Texas. All right. 好，我们要讲中文了。就是我发现我在就是2022年的9月的那个固态热力学，我放了这张照片在最后面。然后我刚刚看到，我就可以跟大家分享一下哈，就是我那时候2022年的时候在美国哦，我就是我去投靠拜访一个学者，就是但是他是我的好朋友从国中开始到研究所都是同一个学校哦，那我跟他是非常非常好，然后他现在在美国的德州农工当教授，那我就在2022年左右的时候去投靠他去啊。就访问他，然后去做一些合作。那时候德州啊，就大陆型气候应该是这样讲吧，我也不知道，反正就是它热就很热，冷就很冷，冷就蛮冷的。然后天气很晴朗的时候，天空非常非常的漂亮。但是当天气不好的时候，就超恐怖的，然后还会有那个龙卷风这样。那我在那边的时候就发现就遇到龙卷风，那还好，当然我没事这样。那这个东西是什么呢？这个东西是有一天呐，就我带着我小孩去公园玩，他们的公园蛮大的，然后有一个这种篮球场，然后它篮球场是有就是半露天，就是应该说半室内啦，就可以看到就只有几根柱子在旁边，然后这是一个屋顶在篮球场，然后去的时候还下毛毛雨哦，我想说还可以吧，我就去，结果到一半的时候，忽然狂风暴雨就来了，超大雨哦，你可以想象，就是一开始都干干的哦，但是我当狂风暴雨的时候，它那个水就马上就淹水，你就可以看到它水就开始一直狂流狂流，而且我就躲在这个篮球场的正中间，因为它雨太大了，所以就算是你躲在篮球场的正中间，你还是会被雨淋湿，因为风太大，雨太大，所以我就跟我小孩躲在这里，躲在就是篮球场的正中间。结果发生一件事情，我那时候真的觉得我就是快要死掉，我觉得很恐怖。为什么？因为他们的雷打得太大了，我就可以站在这边就看到这样子当当当。更可怕的事情是，我们很害怕哦，但是我想说，哇，躲在中间应该没问题吧？然后我还想说，我要避开这些水，免得就是当雷打到船电。我不知道这样是不是有可能啊，我不知道。反正我就是在这中间很恐怖就对了。结果这一棵树在我面前忽然爆炸，因为雷劈到那棵树了，就超大一声，真的很像炸弹在你前面这样爆炸。我跟我小孩就是吓得快要死掉了，这样，我真的觉得就是我觉得我们会死这样。然后你看这个树就这样倒了耶，就这样在我前面这样哒，然后就倒下来了，非常的恐怖。对，在我面前，大概就是我这里到后面的距离吧，大爆炸，吓死我了，真的吓死我了。那然后后来就是你看天气好了，第二天就长这样。你看这天气天空 多么的漂亮啊！我觉得美国真的是得天独厚啊哈。当然啦，我们有台风，他们有龙卷风，但是你看这个天空实在是，我到现在还是很怀念。哎，等一下，你看不到我的那个 enlarge，对吧？你看多么漂亮的天空，对不对？然后，但是如果今天一下雨，就是这种程度，哇，哎，你看还可以看得到雨，哎，还可以照得到雨，你看这个雨有多大，然后就就被整棵树就被劈断了，就这样，好，很猛。那为什么会觉得说我会是生死一瞬间呢？因为这雨下太久了，我们得回家吃饭啊，对不对哈？所以我要怎么办呢？但是我的车大概又停在就是停车场，所以它又一直打雷，所以我带我小孩去骑脚踏车嘛，那我脚踏车就放在这里，脚踏车放在这里，然后我要回家了，那我就想说要跑那一段路到我车上，所以我就抱着它跑去车子这样子，然后我在那一段路我就觉得我要跑超快，但因为我怕滑倒，所以又要跑很快，然后又要很紧张，很怕我跑到一半被雷劈死这样。因为它那边都很平啊，就是没有什么障碍物，就没有什么高的东西，所以我在跑的时候我都很担心，就是说我会被劈死的，很可怕，真的。那这就是大自然的力量啊，哎呀，很好玩。那然后还是很建议大家，就是说有机会可以出国，工作或念个书，然后体会一下跟台湾不同的环境，我觉得是一个很有趣的经验，这样子。好，那现在只剩2分钟，我们休息10分钟以后，我们就进入第九个 PDF。All right, so let's see. I will see you after 10 minutes, and then I will enter chapter 9. All right, thank you. Chapter 9. 好啦，最后1个小时，大家加油。然后接下来就要跟大家说再见啦。啊，非常感谢各位的这一学期的配合。好。好，那接下来讲最后一个 PDF9啊，它是OK，so let's get into PDF9. Okay, the PDF9 is about the heat capacity of solids. Oh, finally we got solid, solid in it. You see our course, it's thermodynamics is solid, but actually, wow, it's we talk about solid. Right. So let's take a look. The CV values of the solid. We find that CV value for solid need statistical thermodynamics and quantum mechanics. All right. So classical is not that work. That doesn't work actually. Doesn't work. So because it's difficult for classical thermodynamics result to have a good agreement with experimental results. It doesn't. It's not good. All right. So we need statistical thermodynamics. Dulon and Patty, if they found that CV actually equal to this value for almost every solid. So they approximately estimate the value by treating every atom of the solid as a linear oscillator with 6 degrees of freedom. What does that mean? Because the oscillator in the solid cannot moving around like gas, right? Cannot rotate around like a gas. So they only have vibrational ability, degree of freedom, right? So how many degree of freedom? 2 degree of freedom. 2 degree of freedom for each oscillator. So you have an oscillator. You can imagine that particle, atoms, atom. Atom and atom has the bonding. The bonding can be treated as an oscillator. So each oscillator has 2 degrees of freedom. So if you have one particle, you will have one particle or atoms. If you have one particle, you will have frontward, backward, left and right, and up and down. So you have 6 oscillator, and in averagely, each atom has 3 oscillator. So 3 times 2 equal to 6. So you can see 6 degree of freedom for each atom. All right. So we're half kT for each degree of freedom. So your CV equal to 6 over 2 R equal to 3 R. And it's called Dulong-Petty value. Okay. 3R, CV equal to 3R. And it is about 2.49 times 10 to 4. Okay. However, CV depends on T. So actually CV is changing. So, and CV becomes 0 as T approach to 0K. So it's not always this value. So you can imagine that this it should be looks like this. Okay, when temperature going to 0. And this is not Dulong-Petty value again anymore. So this is temperature, this is CV, and yeah, so we cannot find. I mean, we need to find a model or a theory to explain this. And also, the CV in the solid decrease gradually with T, but no stair like diatomic gas. No. Okay, so we cannot use exactly the same theory from diatomic. We need to invent a new one. OK， 好，我们这讲说，我们现在看 heat capacity CV 在固体里面，我们终于讲到固体了啊，所以我们叫做固态热力学啊。好，那所以我们应该我在课堂一开始的时候我们就说，这不是固态热力学，这叫做统计热力学跟传统热力学，好，这是在一起的。OK， 好，那我们到这边终于讲到 solid 固体了。那我们再看到就是说，这固体啊，我们需要统计热力学或是量子力学来解释，那比较符合现象。那如果只有纯粹靠传统热力学的话，就比较难好，然后接下来呢，杜隆、Petty 这2个人，他在1819年的时候发现 CV 这个值几乎是一个定值，对于所有的固体来说。然后他们就在想，到底是怎么一回事呢？他们就解释说 ，OK， 应该是 每一个 oscillator 每一个振动子每一个弹簧它只有2个 degree freedom。我们可以想象固体里面它不能移动嘛，不能乱移动，也不能乱转，所以它没有 translation 跟 rotation， 那它们就只有振动。然后那振动，那它振动的话就是有2个 degree of freedom。那振动为什么这边会是6呢？6个 degree of freedom 呢？因为你一个振动子是2个 degree of freedom， 但是你会一个 atom 会有平均会有3个。原因是什么？我刚刚讲到，就是说今天有个 atom， 它前面有个弹簧，后面有个弹簧，左右上下各就总共6个弹簧在前后上下左右嘛，所以平均来看 atom 就会有3个弹簧。那3个弹簧每一个有2个 degree of freedom， 所以就会有6个，所以 degree of freedom， 所以就是 Cv 等于6除以 2r，OK， 然后就变成 3r， 这个 3r 就是这个值。好，那这就是我们的 Dulong Pettit value， 也就是说，它看到都是一个定值，当然不对啊，在温度变小的时候，它就变成0了，所以我们要想一个办法来解释它，想一个模型来解释它，或是一个理论来解释它。但是又不能直接拿刚刚前一个章节看到的diatomic 的方式来解释它，因为它没有阶梯式，它就是一个平台跟一个渐进往下，就这样而已啊，所以跟diatomic 又不一样，所以我们要新做一个东西出来。So the first model is Einstein model since 1907. All right. It's a collection of microscopic systems that can store any number of energy units. All right, so you can imagine that a solid is a collection, many oscillator system. 1, 2, 3, blah, 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 4. To n oscillator. Okay, and each oscillator is a storage of energy. Okay, and each energy unit has the same size, of course, and for harmonic oscillator, no problem. And every evenly spaced energy, of course, you have oscillator, right? So energy is equally spaced for each energy level, no problem. And most importantly, Einstein solid is a collection of n such oscillator and assume all the oscillator has the same vibrational frequency. Of course, you see, this is not good, right? This is not good. But, well, this is the first one, ancient model. So let's learn that first. 好，我们就先讲爱因斯坦模型。他在1907年的时候做出这个东西。他说叫什么？每一个就是固体，我们可以想象它就是一堆弹簧在里面。那弹簧它会储存能量，那边震动，然后那量子力学的震动弹簧，它就是我们之前前一个章节有讲到，前一个 PDF 有讲到，就是它大概是这样。然后它每一个间隔都是 equally spaced， 就是同样的间距 h nu 嘛然后还别忘了它有1/2 h nu 的最0 point energy 0点能量，就是这个特征都还是有然后它有 n 个 oscillator，n 个振动子。那这边很重要的是，它假设每一个振动子都有一样的 frequency。OK， 好，那当然这是不好的但是没关系就先学看吧它毕竟它比较早嘛OK, next. So the Einstein solid model is actually the bead spring model， 就是ball and spring. All right, connect together just like what I draw in the right hand side. All right, 6 degree of freedom per atom. Why? Because 3 for kinetic energy and 3 for potential energy stored in the spring. And we know that energy, each atom has 3, averagely has 3 oscillator around it. So atom can oscillate in 3 independent directions, x and y and z, of course, and an oscillator for n over 3 atom. Yeah, you can see if you have n oscillator, which means that you have n over 3 atoms, or you can say n atom for 3n oscillator. Okay, so normally we choose this. We choose this expression because normally we will say n stand for number of particle, right? Number of atom. So normally we will pick up this n atoms for 3n oscillator. Okay? And harmonic oscillator with a potential energy function half kx squared. Of course, half kx squared is how the spring store their energy, right? So half kx squared. K is spring constant. Okay. The natural frequency of the oscillator. Okay. Here is f equal to 1 over 2 pi k s divided by n. Okay, here is a natural frequency, the resonant frequency. Okay, the resonant frequency typically related to 1 over 2 pi ks over n square root. So you can imagine a resonant frequency. If you have a tougher spring, your resonant frequency will be higher, right? Or if you have lower mass, lighter mass of the spring, it will vibrate faster, right? So this is resonant frequency. By contrast, inversely, you have a loosened spring. The K is small, so it will vibrate slower. Or you have a heavy mass, you will vibrate small. Okay, so the oscillator's natural frequency will related to this equation. 好，我们要讲的是爱因斯坦模型哈。那这个模型它使用球跟豆豆跟叫什么弹簧的模型来看，那就长这个样子。好，你可以看到一颗前后左右上下嘛哈。然后刚刚讲过，一颗 atom 就 share 分享3个，平均来讲分享3个弹簧。那我们都前面不是说 n 个弹簧的话，就会有，其实就表示说这个系统里面有 n 除以3个原子嘛，对不对哈？但是我们通常都会反过来讲，我们都会说有 n 个原子，对不对哈？我们常都用 n 嘛 ，n 代表原子，我们都讲 n 原子，所以呢就会有3n 个 oscillator，3个 n 个弹簧哦。所以虽然一开始的时候我们说 n oscillator 会这样，但实际上我们之后在用到的时候，通常我们都会说以 n 当主角，然后我们的 oscillator 弹簧都是3倍的 n。OK， 好，我们会使用这个说法哈。然后 oscillator 它的能量最容易嘛，就是高中都算过了，1/2 kx 嘛，对不对哈？这个 k 就是我们的弹簧常数 ，x 就是它的变形的量，对不对哈？不管是压缩跟伸长都会平方，让它变成储存它的能量，只要是它不是它的平衡状态的话。然后接下来呢，这个共振频率 （natural frequency） 共振频率，自然频率，是什么东西呢？我们可以想象一下，它的自然频率就会是这个式子。那这个式子你可以看到 Ks 跟 n， 它的分子跟分母的状态。我们可以想象 Ks 就是弹簧常数嘛，很硬的话 Ks 就很大，很硬的弹簧你就会有更高的频率共振频，或者是你的那个质量很轻，你质量很轻的话，你也会振比较快所以它在分母。那反过来讲，你的 Ks 如果很软，它就会慢慢的振动低频。 然后 m 如果很重，它也会低频啊，所以说它都会跟你的风振频有关系。Alright, so 3D oscillators. Let's continue. So let's take a look. So the textbook equation 15.18. Okay, in the equation 15.18, they talk about one-dimensional oscillators. But now we are, so 1D oscillator has the U in here. Okay, but now we are going to have three of them, three-dimensional. So we need to times 3. Okay, so that's how this work. So in the textbook 15.18 is the 15.18 equation, writing down 1 du, but now we are 3 du oscillator, so we times 3, so 3 nk blah 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 blah. All right, and then we also know that z equal to this and u equal to this. Okay, and now because this is Einstein method, Einstein model, so previously theta become is a characteristic temperature. We now adding E on the subscript to make sure this is theta E is talk about Einstein model, Einstein temperature. Okay, and we said H nu over K is H nu over K is theta E. So now we have U here. We can directly get CV, right? CV equal to 3 nk theta E over T square exponential theta E over T exponential theta E over T minus 1 square. Okay, so this is the result, and you can also compare. You can compare this equation with equation point 15.9. So, it's a 19.9. Wow, should be 19, right? Yeah, because this is 18. Suppose the 18 is U, suppose 19 should be CV. Why here I said 9? I'm not sure. OK， 好，就是我的小抄写15.9，可是我这样看，哎，不是15.18是 U 的话，下一个不应该是15.19吗？那怎么会写 U？ 好，你这边回家自己看一下哈，要么就是9，要么就是19。好，sorry， 我只觉得怪怪的。All right, so you can compare this, but you can see that just the three coefficient different. So now you have CV like this. Let's do exactly the same things for PDF 8, high temperature, low temperature. So this high temperature is that the theta E over T is much, much less than 1. Okay, so you can see that so at this let me take a look. Okay, so you can see we see this before. We see this in PDF 8, page 10. The result will be theta E over T square 1 theta E over T squared. Okay, so actually we see this at the condition theta E over T much less than 1. And then we see this condition in page 10 in PDF 8. And it will cancel each other, and the CV becomes 3NK. All right, so 3NK, again, very similar to NR3 times 3. And this is Dulong-Petit value. Very good. Okay, so which means that Einstein model in a higher temperature condition, the CV result is matching the value of Dulong-Petit equation, the Dulong-Petit value. That's good. For low temperature, vice versa. Sorry. By contrast, theta E over T much greater than 1 for low temperature, right? For low temperature, we substitute this condition to here, and we find that this is ugly. But don't worry, because this is again a green function. Well, green highlighted function, not green function. Green highlighted function, and it will reduce if theta E over T much greater than 1. So it reduces to 0 when when T equal to going to 0, CV also going to 0. All right, so you see CV also equal to going to 0, and it matched experiment, right? So this is good. So this model can explain CV at high temperature and low temperature, and the value are all matched. That's good. Okay, and we found that CV over N depending on theta E over T. Okay, and also we can say CV equal to CV divided by N times, okay. Here, don't forget that CV and CV is a little bit different when divided by N times NA. Okay, you see here the CV and CV is a small letter and capital letter, right? So the capital letter divided by N is the CV small letter. All right, depends on theta E over T. Okay, and right, that's it. Oh, I forgot to write down here PDF 8, page 10 is where the green highlighted function curve. OK， 好，我们现在要解释一下，就是我们实验室用爱因斯坦模型，它使用的是3维的振动子。那3维振动子我们要写，就要算它的 heat capacity 嘛。那 heat capacity 之前要算 internal energy 内能。好，那我们看内能怎么算。其实不用那么麻烦，因为我们在课本上15.18的式子上就已经写出了1维的 U 了。那其实就是振荡子嘛，对，然后1维振荡子不就是前一页吗？哈，前一个 PDF 做出来的东西，它就是1维的振荡子。我们现在是3维的，就乘3就好。OK， 那乘3出来以后，我们别忘了要把西塔改成西塔1，因为现在是爱因斯坦模型，我们就把1写上去，证明也告诉他说这是爱因斯坦模型是沙里的东西哈。好，然后这边 U 写完了，接下来就要对它做微分。微分做出来长这个样子，好，很丑，那没关系，你可以看到这个3还在这里，那还是可以去比较一下15.19吧，哈，应该是19的 CV 的值是多少？好，那我们比较完以后，一定就差3了哈。好，然后呢，我们这个就可以把它看高温跟低温的现象的行为是什么？那高温的现象的话，就是西塔1除以 T
远小于1嘛，哈，那这时候我们就可以用我们这个其实遇过了，好，我们在PDF A 的第10页，我们就有遇过，这边会变成这样子 ，OK， 然后它就是就去掉了，然后就变成3NR。OK， 那3NR 就是高温的时候就是3NR，那不就跟 Dulong-Petty 的值是一样的吗？很棒，我们在高温的时候验证它是正确的了。然后低温呢？低温的话是西塔1除以 T 远小于1嘛，远大于1，不好意思，远大于1。那 T 因为 T 很小，那所以我们就发现上面这个式变成还是很丑，还是很丑。那怎么办呢？那我们就写就是我们就发现这个绿色的东西，绿色的荧光笔的东西，其实是在第8的 PDF 档的第10页里面，我们是画一个图，那绿色的 highlight 的荧光函数，它在高的西塔1/T 的时候，它会就是接近为0嘛，哈。好，那所以说它这边就是接近为0。那 T 到很小的温度的时候 ，Cv 也会变得非常的小，变成0。那我们可以发现，爱因斯坦模型在高温、低温都跟实验相符，所以是一个很棒的模型。好，现在看起来好，然后呢，我们就会看一下 Cv 除以 N depends on 西塔1/T 了哈，我们就可以看得出来，用这个东西看得出来哈，就是不对，这个可以看得出来 ，Cv 会跟你的西塔1/T 是有相当的关联。那这边的 Cv 除以 N 其实就是 C 小写 v 乘上 Na。好，那它就是只是跟大家提醒一下哦，就是小写的 v 跟大写的 v 有什么差别？还记得吗？大写的 v 就是应该说小写的 v 就是大写的 v 的参数除以它的个数质量这样。好，那接下来下一页。So now Einstein solids, very good. We have the oscillator frequency. The frequency is this one, right? Again, I just talked about this lighter element, which means that you have a higher frequency. And also means that you have a harder crystal. Okay? Okay? And if theta E/T is large, which means that it's low T, all the atoms are in the ground state, right? And vibrational degree freedom are not excited, so Cv go to 0. Very makes sense, right? But if you have a higher temperature, it agree with classical value. Okay, so this is a really good theory, really good model for Einstein model, right? That's good. 好，我们现在讲一下，就是我们从这边可以看到什么？爱因斯坦的模型，因为它的振动的频率跟 kappa 跟 mu 有关。kappa 就是它的 constant 嘛，就是它那个弹簧常数嘛，哈。mu 就是它的质量嘛，哈。那轻的质量会导致高的 frequency， 那通常也等同于它有比较硬的、比较强壮的 K 的hard 就是比较硬的 crystal。那接下来就是刚刚我们解释过了哈，就是在温度比较低的时候，它会是0，然后在温度比较高的时候，它就会得到 Dulong-Petty 的值，所以跟你的叫什么传统理论是一样的哦，所以是个不错的模型啊。现阶段来看。Now, we are saying that Einstein solid is good, right? However, still have some disadvantage. Why? Let's take a look. So when we write down, do the experiment, and then we found that if we measure different metal or different solid, like PB, AG, something. Actually, if we draw the CV here and X is T over theta E, okay, if we draw the figure in X direction has T over theta E as a ratio, right? And then we find that they are all aligned in this curve. Very interesting. And also we notice that, for example, here, for example, if we have a point with the same ratio, theta E over T, for example, here, triangle is copper, right? And dot is Ag, is silver. And they have the same point, the same value, the same point. And we will say they are in a corresponding state. Well, this is not a really important thing, but just corresponding state. Just give you a terminology explanation, all right? So if they have the same CV, the same ratio, but different element, they may have the same CV. But you can see that because AG and CU has different theta E, but in different temperature, when they have the same ratio, they will have the same the same CV. So we can say this is corresponding state, even they are in different temperature. But as long as their ratio are the same, theta E over T ratio the same, they will have the same CV. Interesting. All right. Now, so we will say these two points are in the corresponding state. Then, and then if we take a closer look to the 0K, we find that this dot are major result, but the dashed line is the Einstein result, and Einstein result give lower CV, which is not good. We are going to change it. We are going to improve it, because the main problem lies that assumption has that single frequency are assumed. Okay, as we said, all the oscillator has the same vibrating frequency. This is not good, right? Never so ideal like this. So it leads the value near the 0K is lower than experimental value. 好，我们来看看，再看一下爱因斯坦模型哈。当我们实验在做的时候，我们会量不同的金属嘛，对不对哈？然后我们发现，如果今天我们的 x 轴，我们使用的是西塔 E over T over 西塔 E， 是用比值的状态来看的话，我们会发现它们点都会落在不同的，就算不同的 material， 它会都坐落在这条线上，非常的有趣。然后这边就可以看得到，就算是不同的材料 ，AG 跟 CU， 它们有不同的西塔 E， 但是它们在不同温度下，只要有它们的比值是一样的，西塔 E over T 这个比值是一样的，它们就会有得到相同的 CV 哦。所以这还蛮有趣的。那我们叫它这样子的状态为 corresponding state。OK， 那只是一个名词而已哈，跟大家解释一下。那接下来呢，爱因斯坦的模型，我们发现它有一个 不好的地方就是它在靠近低温的时候，它的 CV 我们的估算会比较低，爱因斯坦的 CV 会比较低啊，这为什么呢？就是因为它只假设一个 frequency，好，那就是它没有很好的地方。好，那接下来我们就要去改善它。We're going to improve it, but before we improve that, we need to do a example before we enter the next the by model. Okay, I guess the by model should be in our video next week. All right, but I hope I can finish this example today. So this is an example for Einstein model, right? So the partition function of a system that obey Boltzmann statistics. Boltzmann statistics, what does that mean? It's oscillator, right? Oscillator. Okay, and it's given by Z. Wow, this is a new material. Okay, the problem define a new material, give you Z equal to these things. And you can notice that, okay, theta E over 2T. Okay, so theta E is Einstein model, no problem. Where A is a constant, okay, and theta E, H nu over K, calculate U, P, F, and CV. Okay, let's take a look. Z is AV squared exponential minus theta E over 2T. So if we get Z, normally we'll get natural log Z because U is needed, right? Natural log A plus 2 natural log V minus theta E over 2T. Okay, so this is natural log Z. So the first one, of course, not too bad. U equal to, okay, this is important. Now, previously, our U is NKT squared partial natural log Z over partial T, right? When you write down the oscillator in diatomic gas, right? We write down this, but now, don't forget, this is three-dimensional now. 3 oscillators, okay? So it becomes 3. So be careful about this. 3 NKT squared minus theta E over 2 minus 1T squared 3 over 2 NK theta E equal to 3 MR theta E over 2. Okay, so this is U. Don't forget the 3. Next, UPFCV, right? So next should be P, right? But remember that our P came from F, right? So actually, we are not going to determine P first. We need to go for C from F first. Okay, so be careful. The order of the properties. Now, another important thing is that this is minus 3 NKT natural log Z. This is so important. This is so important, all right? I know this is different from what you memorized because this is previously is one-dimensional Maxwell-Boltzmann, right? Previously, but now, actually, this F is the problem 15.2. I encourage you to do the problem 15.2 to get S first. Of course, your S is from K natural log W, Boltzmann equation, right? and then you get F. C PDF 6 P23. Actually, this procedure is not new. Okay, we have taught this, we have introduced this. So you see the PDF 6 PDF 6 page 23, but really important. Previously, it's one-dimensional Maxwell-Boltzmann, but now this is three-dimensional Boltzmann. So different. We need to use the same procedure, but the hint is three-dimensional. Okay? What is the difference between the three-dimensional and one-dimensional? The first one is your N becomes 3N. Okay? But your G is still G. It's so important. All right? When you do your S, do the S to get your F. The procedure is the same. Okay, no problem. But previously, this is one-dimensional Maxwell-Boltzmann. But here, you are going to have three-dimensional Boltzmann. So previously, in that problem, your N need to be changed to 3N. But your G is still G because your oscillator, the only thing that changes oscillator become 3 times. 3 times. But the G is still the same. The oscillator is still the same. So the degeneracy of this is still the same. So you use these two things, follow the rule, you can get this. So this is really important. All right. Minus 3nk t natural log A plus 2 natural log V minus theta E over 2t minus 3nkt natural log AV square minus theta E over 2t. Okay, so I guess I will stop here. Okay, and I will left things for the video. Okay, but now I'm going to do the Chinese translation now. 好，我们要就是爱因斯坦的模型讲完了哈，接下来我们要做个例题。这个例题我觉得很重要，所以我一定要先在这边讲而且我最重点在这里，我也要用中文跟大家讲一下哈。就是说，这个 partition function 是一个新的材料，这个材料写 z 这写了一个很奇怪的式子，不管它遵守 Boltzmann statistic 就是振动子的那个 statics 嘛哈，统计。好，那这时候我们就说要请他，我们有这个 z， 我们要算 UPFCV， 好，我们就来开始算这个 U 呢，就是一般的 1D 乘上3这个应该没问题吧哈。我们就把刚刚的 natural log z， 我们看到 z， 我们就先算一个 natural log z 哈，因为应该大家都还蛮熟的哈，就直接 U 就直接要用 natural log z 嘛哈，算出来以后带入这个得到这个东西，这个应该没有问题。好，接下来呢，第二小题它要我们算 P， 但不要被骗，因为 P 其实就是从 F 的就是 partial 来的嘛，对不对哈？所以我们不要先算 P， 我们要先算 F 好，我们先算 F。先算 F 又麻烦的事情是，我们算出 F 其实要先用 S 来算，要先用 S 来算，所以它这个题目很坏就是先问 P 又先问 F， 但是他没有叫你算 S。不管怎么样，我们先算 S， 然后从这边算出来 S 可以就是应该说啦，就是这一题其实就是在 15.2 的例题啦你就可以算 S， 然后再算 F。好吗？好，然后呢，我们 S 算出来 ，F 算出来。其实这件事情，这个过程，数学过程并不是新的哦。我们在第6个 TPDF 的第23页，我们就跟大家带过从 S 算到 F， 这样算出来咯。但是这边有一个非常重要的事情是，当时是 Maxwell-Boltzmann 的一维的，现在是三维的 Boltzmann。好，所以这边要小心。我们同样的流程，但是里面有几个东西要改一下哦。一个是 n 要改成3n， 因为原本是 n 个嘛，现在改成3n 个 oscillator。那为什么不能？就是当然你在算的时候，你就会发现这样子改，因为就是 u 这个东西是用加的，所以就还好。可是因为这边 s 啊 f 啊，它会那边微分来微分去啊，乘来乘去，所以你不能直接就不能把结果乘以3，这边会变成-3。好，那还蛮特别的。好，所以 NKT natural log z 这边要小心，就是跟我们背的不一样。好，那是因为我们要把 n 改成3n。另外一个最重点就是 G 还是 G 哦。我曾经看过学长 G， 然后跟那边改成3G 就不行。为什么？因为你的弹簧变成3维，你只是多了3倍而已。你不能说弹簧也变成三倍的，就是3倍的选择权，不可能吧？同样的弹簧啊，所以 G 跟 G 是不会变的，但是个数会变。那这些东西课本都没有讲，哦，实在是太厉害了，好，要让天才自己想出来哈。那这边跟大家提醒一下，回家把15.2算一算，然后你就可以得到 F。你理论上来讲，你会得到这样子的 F， -3NKT natural log z， 然后这样子就直接带进去就好，然后得到这个答案。那一样，接下来就是做一些积分，就做一些微分就可以得到 P， 然后你的 CB 再把这边微分做出来得到答案。OK， 所以基本上这一题的最重要的地方就是这里了。好，我认为，所以做这题之前先算一下15.2，那一定要算哦，因为你到期末考的时候啊，一定会有不一样的，就是这些 U 啊、P 啊、F 这些，你不能用背的啊，你就要仔细的去辨认它是三维的，它是一维的，还是怎么样 ？OK， 这边要小心。那我想接下来我就交给我自己的那个 video。我会传到我们的YouTube channel，然后请大家就是仔细看，然后应该没有多少哈，只剩下10几页而已。那我们这一个学期的课程就到这里结束。那谢谢大家，然后17号要期末考，好，那就这样子。如果有问题来问我，谢谢 ，Thank you，Bye，Thank you for your cooperation，拜拜。